To make any physical system move faster, you have to add energy. You turn up the heat, you apply more force, and the resulting speed increases. That is the baseline rule of thermodynamics. But in the late 19th century, chemists like Svante Arrhenius observed laboratory reactions completely breaking this rule. They watched chemical processes speed up dramatically, while the total energy input to the room remained completely unchanged. Arrhenius proposed that molecules face an invisible energetic hill they must climb before they can react. He called this activation energy. Activation energy is the minimum amount of extra energy molecules must possess to successfully break their existing bonds and form new ones. Without enough heat, the molecules simply bounce off the hill. Yet experiments continued to show an impossible result. A massive volume of molecules was suddenly pouring over the barrier. The reaction was accelerating, but the thermometers showed no added heat driving them. If thermal energy wasn't physically pushing these molecules over the peak, the scientific understanding of chemical speed was missing a hidden structural mechanism. We can isolate this mechanism by simulating a standard hydrogen peroxide decomposition. In a controlled environment fixed strictly at 25 degrees Celsius, with a concentration of 1.0 mole per liter, hydrogen peroxide breaks down and releases oxygen at a slow, measurable rate of 0.5 milliliters per minute. This graph compares that baseline oxygen release against what happens when we introduce a tiny amount, just 0.01 moles of manganese dioxide as a catalyst. Keeping the temperature and concentration exactly the same, the oxygen release spikes to 25 milliliters per minute. The system is operating 50 times faster with zero added heat. The only mathematical way to resolve this is to revise our understanding of the barrier itself. The manganese dioxide isn't adding energy to push the molecules over the mountain. It is physically lowering the barrier from 75 kilojoules per mole down to roughly 25 kilojoules per mole. But look closely at the total energy released. In both the slow reaction and the 50 times faster reaction, the starting and ending states remain perfectly fixed at negative 98 kilojoules per mole. The catalyst provides no fuel. Instead, it acts as a molecular architect, carving a highly efficient, low-energy detour through the existing energetic landscape. To see how that detour is built, we have to look at the microscopic mechanics. In a standard reaction, molecules collide roughly 1 million times every single second. Without a catalyst present, the vast majority of those impacts are useless. Only about 0.01% of the random collisions possess the exact speed and precise physical orientation required to react. This distribution curve shows the probability of a successful collision. When the catalyst enters, it physically grabs the molecules, altering the orientation and creating intermediate states. An intermediate state is a highly reactive, temporary chemical structure that forms briefly before the final products are made. By forcing the molecules into these perfect alignments, the success rate jumps to 5%, a 500-fold increase in efficiency. If this substance is physically grabbing, bending, and reorienting millions of molecules every second, you would expect it to be rapidly destroyed by the friction and bond breaking of the process. But if we track the mass of the manganese dioxide over 60 minutes of violent reaction, a starting mass of 1.000 grams ends at exactly 0.999 grams. Factoring in measurement error, the mass is entirely intact. Catalysts are temporary pathways. They engage with the molecules, force the chemical reaction to occur, and then instantly detach and regenerate, surviving as immortal participants in the system. This invisible manipulation scales up to massive industrial applications, most notably in the Haber process. The Haber process is a manufacturing procedure that combines nitrogen from the air with hydrogen gas under high pressure to synthesize ammonia. Left alone, breaking the bonds of nitrogen and hydrogen requires a stubborn activation energy of 250 kilojoules per mole. By introducing an iron-based catalyst into the reactor, engineers drop that barrier down to 150 kilojoules per mole. Under identical temperatures, a reaction that was previously too slow to be useful suddenly yields tons of agricultural fertilizer every single day. The exact same mechanics govern human biology. Our bodies rely on enzymes, which are specialized biological proteins that act as organic catalysts. They fold and bind molecules within our cells, accelerating those processes by factors of 1 million, allowing slow metabolic reactions to happen fast enough to keep us alive. Mechanical engineering uses this too. Inside a car's exhaust system, a catalytic converter physically forces toxic nitrogen oxides into new molecular alignments, neutralizing harmful emissions in milliseconds before they leave the tailpipe. Chemistry is often viewed as a brute force exercise of applying heat to break bonds, but the design of these materials proves that true control comes from defining the molecular path, allowing the universe to take the path of least resistance.